Alright, so this is my first video in the vector calculus series, and I will be beginning by talking about parametric equations of lines. Okay, so we're in three-dimensional space here. I have my three-dimensional Cartesian coordinate system, and I'm asked to find the parametric equation of the line through points P1 and P2, where P1 is the point 4, minus 1, 2, and P2 is the point 1, 1, 5. Okay, so this point right here is P1. You can see that it's 4 along the x-axis, minus 1 along the y-axis, and then up 2 in the z direction. And similarly, P2 is right here. Okay, so how do you find the equation of a line in three-dimensional space? In two-dimensional space, you have something like this. Y equals mx plus b. But in three-dimensional space, if you were to plot this, you'd have a line down here in the xy plane, and since z doesn't appear in the equation, you actually have a like a three-dimensional surface where when the surface crosses the xy plane, you have this line in the xy plane, but then it extends up and down in the positive and negative z direction. So an equation like this isn't going to work in 3 dimensions. Okay, so instead what we do is we say, okay, I'm going to have a position vector that goes from the origin to some point on the line, say some point P on the line, and this position vector is going to be a function of some parameter that we're going to call t. So basically, we're going to say that at different values of t, this position vector is going to point at different spots along the line. So maybe when t is positive, the position vector points in this direction along the line, and maybe when t is negative, the position vector points at, I don't know, somewhere down here. Maybe at t equals 0, it points at P or P1. Okay? So actually, let's say that this position vector points at P1 at t equals 0. So we said that at t equals 0, our position vector points at P1. Okay, and we said for this example that as t increases, maybe our position vector moves along the line in this direction. Okay? So if we call this vector vector v, we can actually come up with a vector that points in this direction. We can actually come up with a vector that points from P1 to P2. Okay? So if I write that like this, if I call v the vector that goes from P1 to P2, well, the way I do that is I take the x component of P2 and I subtract from it the x component of P1. Okay, so vector v would be, I'm going from P1 to P2, so it would be 1 minus 4. So 1 minus minus 1 is 2, and then 5 minus 2 is 3. Okay, so this is the vector that goes from P1 to P2. And if you're not sure how that works, I guess I could just do a quick example. If I have a vector A and a vector B, and I want to find vector C, or in this case, C would be vector V. What's this here? If I use basic vector addition, A plus C is going to equal B. So if I'm trying to solve C, which is similar to what I'm doing in this case, you see there's another vector here that goes up to P2. This is the one that goes to P1. There's another vector that goes to P2. So this vector here plus V is going to equal P2, which is similar to what I have here. And if I'm solving for c, I just subtract vector a from both sides, and I have c equals b minus vector a, like that. So pretty straightforward. Okay, so let me ask you a question. If I had some number, we'll call it that, I meant to write an a, but whatever that is, if I had some number multiplied by v, then essentially what do I have here? Well, I have a scaled factor of this vector. So if this little symbol here is 1, then I have the vector that goes from p1 to p2. But if it's a half, then that means that I have a vector that goes from, let's say, here to here. Okay, so let's just say that that is this little swirly thing times that. Okay, so now what happens if I add p of t plus this scaling factor times v? What do I get then? Well, I just get a new vector. Well, I probably shouldn't have put that in that spot, but I get a new vector that points from the origin up to that point there on the line, right? So, like what I just said, it's a basic vector addition. This vector p plus this vector, which is a scaled, the vector v scaled, I get this new vector, so I'll just call this new vector, I don't know, w. Right, so p plus this number times v equals this new vector w, which is on the line. If that scaling factor is greater than 1, then I have some w be some point up here, because this new vector here would extend from p1 up until a point somewhere along the line that's past p2. So hopefully that wasn't confusing. What the hell is happening? Okay, so that's how you parameterize a line in three-dimensional space. You essentially say that my vector pt, okay, let's give it a starting point. Let's say that it starts at the point p1. Okay, so p1 with the little line on top, that's a vector that goes from the origin to p1. And then I add to that some scaled factor of this vector v. So you see this position vector is parameterized, and it depends on this variable t, and t is actually this scaling factor that I'm using to scale v, which is what they call like a direction vector. It points in the direction of the line. So at given values of t, I end up at different points along the line, whether it's in the direction of v or in the opposite direction if t is negative. So the way you would write this, I guess, the final answer in vector form, is you would say that this new position vector, which is a function of t, I'd write it like this, starts at the point 4, 1, and 2, and then at different values of t, it extends in the direction of v, which we said was -3, 2, and 3. And you can see that at t equals 0, you're at your starting point p1. At t equals 1, where do you end up? Well, you just do the vector addition here, component by component. 4 minus 3 would be 1. Minus 1 plus 2 would be positive 1. And then 2 plus 3 would be 5. So when t is 1, you end up at p2, which we also said was on the line. So you can see that at different values of t, you end up at different points on the line. And this is the vector form of a parametric equation for a line. And you can also write it in the component form, where x equals, well, what are the x components here? 4 minus 3t, y. What are the y components here? Minus 1 plus 2t. And what are the z components? 2 plus 3t. Okay, so these are the scalar equations, and these are the vector equation, or this is the vector equation.